And then the original question was about the limiting values of the vectors. If you keep applying this matrix, starting with any vector, if you start here, for example, you might jump to here, and then to here, and then to here, and then to here, and then to here, and the vectors bunch up on this side as we saw before. But in this case now they bunch up along a straight line. So to do a more accurate picture, all these vectors ought to end up on the straight line, okay? And the line goes from 1,000 here to 1,000 here. And then here they do the same thing. So here's your limiting population. Well, it should just go to the line, but you get the idea. So that's a picture we looked at last time.
So every matrix has vectors?
Every stochastic matrix will behave like this.
Okay, and you get
And the
vectors.
eigenvalue, you'll always have an eigenvalue 1. If you factor this thing, and factor the discriminant and get what you get like an r plus s minus the quantity, plus or minus the quantity, r plus s minus 2. Well, when you have the minus the r plus s minus 2, you get a plus 2. Divided by the 2 in the denominator, you get 1. So whether you understand that or not, if you just write out those solutions that you've already written out, most of you, okay, you get an eigenvalue of 1, always. And that eigenvalue will always tell you when you go through a certain other step that we haven't gone through yet. It's a pretty easy step, okay? That'll always tell you what your stable configuration will be, or at least what line that stable configuration will be on, depending on how many people you have in your model, okay? If you have 1,000, then it's this line, it's 1,000 here to 1,000 here, straight line, okay? Now this other eigenvalue, well, the slope of this straight line is going to be the same as the slope of this other eigenvector, okay? Now you don't need to know what an eigenvector is or how to get it. As I say, it's pretty easy for a 2x2 matrix, okay? Well then, if we do this for a 3-dimensional matrix, what happens? Well, your vectors are going to be in 3-dimensional space, right? So you're going to have like an x, a y, and a z axis, and your vectors are going to be in some direction in space. You can visualize it. And then how do they behave? It's a little more complicated than the way these behave, okay? Which leads to behaviors that you don't get with a 2x2 matrix. Well, there's no reason to stop with 2x2. Like here's a 4x4, right? I mean, you stop with a 3x3, do the eigenvectors of this, right? And they're going to behave in a certain way, okay? You can't graph it in 4 dimensions. You can't visualize 4 dimensions, right? Okay? But you can still do the algebra. And you manipulate the numbers in exactly the same way, okay? And you use your ability to visualize in 2 and 3 dimensions to get a picture of what kind of happens in 4 dimensions, okay? Or in 100 dimensions. So you build on it. If you understand what happens here, then you have a good basis for understanding what happens here. And once you understand this and this, you just kind of use your geometric intuition on these to understand what happens with a bigger one. Okay?